Okay. So what we saw yesterday was that um, given G tree with most K along with a tree decomposition of width at most K, we can solve the maximum weight independent set in what we actually saw was that we can find the size of the maximum independent set in this much time. But if you really want to find the set, and the standard dynamic programming trick, because every time when you are you can just sort of trace back. You go to the root where you get the size, and you get the size from something here plus this. So, and you need some back pointers, and so which set that realizes this maximum that intersects with this set, and you can just pull that out. Okay, so I'll just leave it here as in the same time. By the same token, at least we can find min vertex cover in I'm not saying minimum weight vertex cover, but that can also be done essentially mimicking the same dynamic programming algorithm. But min vertex cover follows immediately, because if you look at the unweighted version of the problem, you can find the maximum independent set in that much time, because we really did not use weight or put all the weights to be 1. What you're looking for is a maximum independent set. You take the complement, you get the min vertex cover. Now it turns out you can solve a number of minimum dominating set in something like 4 power k. Actually, it can be improved to 3 power k. 4 power k, there's a big description in the book, and a whole lot of problems. Okay. Essentially mimicking this dynamic programming. The way they differ is that in the case of independent set, all it mattered to find the independent set of this subgraph was that what is its intersection with the bag. We just used that, ran through all possible subsets, and that determined everything. So that was like this 2 power k. Now in other problems, it's not just the intersection. You may want a partition of the bag into multiple different pieces, and how they are partitioned, and so on. So that give rise to different f of k here, okay, instead of 2 power k. So for example, you can find odd cycle transversal in 3 power k, k power order 1, and you can do max cut and there are a whole lot of problems like feedback vertex set in undirected graphs, right? We are talking everything about undirected graphs because this notion of tree width, we've been talking only about undirected graphs. longest path, cycle, testing for Hamiltonian path, cycle, Steiner tree, connected vertex cover, right? You want to find the minimum vertex cover which also induces a connected subgraph, and a whole lot of problems. Now the f of k is slightly different. Connected dominating set, connected FES, chromatic number. These guys, the standard dynamic programming actually has a running time of this. When I say standard, I mean the simple dynamic programming, but there are some of these problems, this f of k can be improved to some c power k. Okay. So these get more involved, so I'm not going to get into it now. So there is actually a very nice general theorem due to Kursel, which says that a number of graph properties which has a certain property can be any property expressible in monadic second order logic can be solved f of k n time on graphs with at most k given the tree decomposition. This is a nice interplay of logic, automata theory, and algorithms. So if somebody is interested, there is a lot on this in various books. People interested in logic can understand it and actually appreciate this better. But this gives you in some sense a template to check whether a problem is solvable in f of k times FPT parameterized by tree width. All you have to do is to take your property and see whether it's expressible in monadic second order logic. If so, then bang, you have. It may not necessarily give you the best f of k. Then you can look at the specific problem and do some algorithm by hand for that specific problem, but at least this gives you a way to quickly check whether it's FPT or not when parameterized by tree width. Okay, I want to emphasize that now parameter is not the solution size, which has been the case for a lot of problems we've seen so far. Here the parameter is the tree width and you're actually trying to find the optimum solution. Okay, so now, so in fact much of today's lecture is some black boxes about tree width more than getting into detail about it. So how do we check this? How do I get the tree decomposition? Again, I'm not going to get into it because that's also involved, and one can take a couple of lectures to describe algorithms which can test this. But it turns out this is also an NP complete problem. Given a graph, to test whether its tree width is at most k, what is the smallest tree width is an NP complete problem. But okay, before that, we didn't address this question. Is the tree width actually well defined? Maybe there are problems, there are graphs for which there is no tree decomposition at all. If so, then you can't even talk about tree width. No? The graph itself. One single bag, right? Okay, so you take one single bag, put the entire vertex set into the bag, that is a tree. It satisfies all the properties of the tree decomposition. Every vertex is covered, every edge is covered, and connectivity, all that. So there is always a tree decomposition whose width is at most n minus 1. Okay, this is useful to know. Okay, so again, it's NP hard. So is it FPT parameterized by K is one of the first, even before the notion of parameterized complexity came in, people have looked at. And what do we know? So there are algorithms 2 power k square. Let me just check. Yeah, computing tree width. K power k cubed. K power k cubed algorithm which, given an n vertex graph and k, will return a tree decomposition of width at most k, or say that no such tree width of G is greater than k. This is sort of an exact algorithm. This is known pretty 90s, I would think. But this is a bad running time even as point of view of an FPT algorithm. But there is some approximation algorithm known, approximation in the FPT sense, which will take 8 power k square n square This is very useful actually, that it's a reasonable running time, 8 power k, single exponential. Either it will say your tree width is greater than k, or it will produce you something whose tree decomposition at most 4k plus 4. Okay. If it produces this, you still don't know whether the tree width is less than or equal to k or not, but it gives you sort of like a 4 approximation. So this is still useful for a, again, so like this, Kurzweil's theorem gives you a way to quickly characterize whether a problem is FPT or not when bounded by tree width. Just check whether it's monadic second order logic expressible. This is also useful. I'll give you our favorite a vertex cover algorithm using this. Okay, an FPT algorithm for testing whether a graph has a vertex cover of size at most k. Right, k is the solution size which we are used to. I will use this to give an FPT algorithm. It's going to be a bad FPT algorithm, but it illustrates something, and we will use it. So your input is GBD, and my parameter is k, and the question is, does G have a vertex cover of size at most k? Let's So, here is my algorithm. Using theorem 1, theorem 2. So, I take my graph, take that k and give it to theorem 2. Two possibilities, right? What do I get? Either it will say tree width is greater than k, or it will give me a tree decomposition of length 4k plus 1, 4k plus 4, right? If this is the case, I can actually find even minimum vertex cover, right? Because we said we can find maximum independent set, minimum vertex cover, all of that. So, find minimum vertex cover in that graph. How much time I will spend? How much time? 2 to the 4k plus 4, right? This tree width. This is yesterday's algorithm. I only promise you an SPT algorithm. Okay. In this case, it's a no instance. There was an exercise I left at the end, right? Why is it a no instance? Did people think about solution for that? So yesterday, towards the end, I said, if the graph has a vertex cover at most k, then its tree width is at most k. If the tree width happens to be greater than k, then it doesn't have a vertex cover size at most k. Why is that? So, as G has vertex cover of size most k implies tree width of G is at most k. So, to show this, what do you have to do? Give me a tree decomposition whose width is at most k. Suppose graph has vertex cover of size at most k. Okay. Right. To make sense of what Manas is saying, what is the tree width of an empty graph, an edgeless graph? Suppose G is a graph which has no edges. What is its tree? 0. Right? What is the tree decomposition with? So, what? How much back size are you allowed? 1. If you are saying tree width is 0, the back size is 1. So, what is the tree decomposition with back size 1? These even have a path decomposition. Right? So, I just V1, V2, V3. Suppose the graph has n vertices. Let's say this is my tree, where this is the back. This vertex has a bag V1, this vertex is bag V2, V3, V4, Vn. Let's make sure that 3 conditions of the tree width properties are satisfied. Every vertex should be covered, it is there. Every edge should be covered, no edge is there, no problem. And you have a connectivity property. Well, there is only one bag that contains a vertex, so it's connected. So, this is a tree decomposition of an edgeless graph where the size of the maximum bag is 1. So, it's a tree width is 0, right. So, now let us come back to suppose the graph has a vertex cover of size at most k. So, what does that mean? So, here is a vertex cover whose size is at most k. What do I know about this induced subgraph? Edgeless, there are no edges here, right. So, I do this tree decomposition for this graph, okay. Insert this set into every bag. Okay. Bag size is k, where k plus 1, and it is a tree decomposition. Why? Every vertex is covered, every edge is covered, because the edges are only incident on these vertices, and every bag contains that. And no, edges are incident, but the other endpoint could be here, right? But that's okay. So, if you have an edge like this, sure, that bag contains this. But if you have an edge like this, then there is a bag that contains this vertex, that bag will contain that edge. So, every edge is covered, and connectivity property, because these vertices are only in one vertex, one of the nodes, but these vertices are on every node, so it is connected. Okay. So, please carefully verify all these three properties, and what we have shown is that if the graph has vertex cover at most k, then take this edgeless graph, compute this tree decomposition, which is this, and then take this set and insert it into every bag. So, that is true. So, now what do I have? I have an FPT algorithm. So, either I will say no, there is no vertex cover of size at most k, or I can find the minimum vertex cover in this much time. Okay. For vertex cover, this is not very useful, we know very efficient better algorithm, but for some other problems, this is still useful. So, the thing is that the tree width is large, then for this problem it is a no instance. Sometimes it can be a S instance. Okay. So, for certain other problems like longest path, for example, if the tree width is large, one can argue that it is an S instance. So, whenever you have this thing that if the tree width is large, either it is a trivial no or S instance, otherwise tree width is small and you have a dynamic programming algorithm based on Kurzweil's program, that is another FPT algorithm paradigm, right. We have seen bounded search trees, iterated compression, branching, kernelization, use Kurzweil's theorem, another template, use this tree width machinery, another theorem where you can do this. Okay. Similarly, for example, we argued that if I, or at least I gave this as an exercise, that if you have a feedback vertex set of size at most k, tree width is at most k plus 1. Okay. Why is that? Same kind of thing, right. You have a feedback vertex set of size at most k, you delete it, what you have is a forest. What is the tree width of forest? 1. Why is that? For a tree we saw it as 1. So, you have multiple trees, and so you can do this tree width thing, and then how do you connect them? Just an empty bag at the root, because there are, you kind of covered all vertices, covered all edges, you have done this connectivity property. So, a forest is tree width 1. So, do a decomposition of the forest, then insert this in every bag, and you have k plus 1 would be the tree width of this graph. So, the same kind of algorithm would work. It is not 2 power, because for feedback vertex set I have erased it. You do not have a 2 power tree width algorithm, but 3 with power tree width algorithm. But anyway, at least it gives you a simple FPT algorithm where you need these big things, right, dynamic programming and bounded tree width graph, and if the tree width is large, either it is a trivial S or no instance. If you have both of these things, you can put them as black boxes and get a good FPT algorithm. Okay, but okay, so we can use this. Okay, to design even better algorithms on special graphs. So, okay, so here is another not a easy exercise. I mean, it's one direction is easy, but tree width of a grid. Let's remember when we talked about maximum weight independence set, we gradually started with trees and then k-by n grids, and then we moved on to tree width graphs. Grid has certain good connections to tree width graph. If you have a T by T grid, what is a grid? Well, you know what it is. It's basically a graph. Think of it as T rows and T columns, and the edges are only across adjacent vertices. Then you can come up with a tree decomposition whose width is t plus 1. That is relatively easy. You can just take one row plus one vertex and drop one and include one and gradually get this tree decomposition. That itself is a very non-trivial exercise, but not hard. But what is hard is to show that there is no smaller tree width. It's actually tree width is t. Okay. Now, again there are some powerful theorems, which is this excluded grid theorem. So, one can ask, what is blocking my graph to have small tree width? Okay. So, I suppose I have a graph which has a large tree width. Can I say then that I have a certain forbidden structure in the graph, and that is why my tree width is large? In particular, if you have a grid sitting as a subgraph in this graph, grid of size t, then you know that its tree width is large, because remember we saw that tree width is of a big graph is k, then tree width of the subgraph is also at most k, right? Because you just delete edges, vertices, and you can keep the same tree decomposition. So a contrapositive of that is that if you have a graph subgraph which has a large tree width, the original graph will have a large tree width. So now can we say something like this, that G has tree width greater than or equal to t, then G has a t by t grid as a subgraph. Well, we can't really say this. We would like to say this, but what we can say is, if G has tree width greater than, I think the current number is some 90 t power 98 plus little o 1, then G has that grid not as a subgraph but as a minor. Recall what a minor is. You have this big graph, you obtain a minor by deleting some vertices, deleting some edges, and contracting some edges. Then what you get is a minor. Again, we saw yesterday that if the minor has large tree width, the graph should have a large tree width. Okay. So let me check this number. I think it's t power 98. So this function t power this was gradually improved. Initially it was some exponential in t. Now it is about 2-3 years ago it got reached t power 98 plus little o of 1. Did I write little o 1? Yeah. This is a theorem. This is 2013. But on planar graphs, we can say something better, which is very useful. We'll see some dramatic results using the excluded grid theorem on planar graphs. Where this can be brought down to actually linear in t. So the proofs of these theorems are pretty involved, but still you can use them nicely as a black box and sometimes design good algorithms. Okay, that's why I want you to know and get a feel for how we can use them. The excluded theorem on planar graphs says that if G has tree width greater than t, then it has a grid minor of t by 9 by t by 9. G is planar and has sorry 9 by 2t. Okay, let me state it as essentially t by 9 or 2t by 9. Okay, so this is useful, this is useful. So okay, one corollary of this is that G is planar, tree width of G is on n vertices, G on n vertices. What is its tree width? I claim it is some c times root n, order root n. You have n vertices. Why? Because if the tree width is larger than root n, 9 by t 2 times root n, then this theorem says it has a root n by root n minor. What is a root n by root n minor? How many vertices does it have? N vertices, right? So how can a minor have more vertices than the original graph? So suppose this, okay, so I can even say it's strictly less than or equal to 9 by 2 square root of n, because if tree width is strictly more than 9 by 2 root n, then this tells you that it has a minor whose size is strictly more than t by t. So root n by root n, but that means the number of vertices in a grid root n by root n grid is n. So you cannot have a minor having more vertices than this. Okay. So here are some interesting corollaries out of this. In planar graphs, vertex cover, I want to find minimum vertex cover. So I give you a planar graph and I want to find the minimum vertex cover. How much time does it take in general graph? 2 power n is easy, but we can do better, right? Yeah, you use any good parameterized algorithm, 1.3 power k, run it from k equal to, so you can do it like 1.3 power n, right? General graph, you can do 1.3 power n, 2 power n. But here, you can solve it in how much time? Why? Root n. So you take your dynamic programming algorithm we saw yesterday, which will run in 2 power tree width time. Now tree width of a planar graph is some order root n, so you can solve it in this is impressive, right? Because you have a sub-exponential, it's still NP hard, but you have an algorithm which you can solve it into the square root of n time. How much time I need to solve the parameterized question? Suppose I care about, in planar graphs, I want to know whether does the graph have a vertex cover of size k. You need to at least use a couple of things you learned. I want to know whether there is a vertex cover of size at most k. I'll give you one hint. Can you bound n? In general graph? Forget planar graphs. I give you a graph and ask, is there a vertex cover of size at most k? Can you? But the question, with respect to my question, is there a vertex cover of size at most k? Is what I want to solve. Please don't tell Saket that you answered this. Okay, can you kernelize? Is there a vertex cover of size at most k? What kind of a kernel can you get? 2k, we even saw it, LP, Nemours or Trotter. So, in polynomial time, I spend in general graph, not even in planar graph, in general graph, in polynomial time, either I will say no along the way, or I will give you a graph with at most 2k vertices, equivalent instance. Now, in planar graph, I can do the same thing. I am not even using planarity here. In fact, this is an interesting question. Is there a better kernel for vertex cover on planar graphs? We don't know. It's an open problem. Okay, better than whatever we know in general graphs. But that's okay. I use the same standard kernelization and get a 2k sized graph where I have to now work further. There I will apply this algorithm. Now n is k. So you get sub exponential time, right? Use 2k kernel and corollary 1, right? This is also very impressive, right? 2 to the order k times, I mean, or plus some polynomial time. But this is to do the kernelization. It has to depend on n. So all this is because of this nice grid theorem, and for planar graph, it is this. Okay. But if I want to do this for feedback vertex set, I don't get such a nice algorithm. I don't get a sub exponential algorithm if I just use the same thing what I did. Let's see why, and then I need to do something else to get that. Okay. So input. So I'm G, but G is planar, and I have a parameter which is k. The question is, does G have an APS size at most k? Okay. So even here, what is an analogous result to corollary 1? If I want just, there is no k, I just want to find the minimum feedback vertex set. How much time? Not 2 power. If you remember my dynamic programming, I said for feedback vertex set, it's not 2 power, but k power. Tree width power tree width, which is still not bad, right? So min FES can be solved in my tree width is like root n power root n. Okay. Order this much time. This is still sub-exponential. Why? Because this is like 2 power order root n log n. Sub-exponential. Okay. So this is like my corollary 1 for vertex cover. I said if I just really want to find minimum vertex cover, we use the fact that a planar graph has tree width at most order root n. So you use tree width power tree width FES algorithm and we get this. Okay. Can I get an algorithm of the second type? Something similar to corollary 2. Not quite, because quadratic kernel is what we have for feedback vertex. We don't have a linear kernel. So you can kernelize it. Given an n, I can convert it to an equivalent instance with k square vertices and edges. Then when I apply this, I still get some 2 to the order k, because square root of k square. So that's not yet sub-exponential, but there is a way around it. Okay, by using this directly. Okay, I won't use the corollary. I'm going to use this and get a sub-exponential algorithm for feedback vertex. So what is this saying? Because this is what I mean by the proof of these theorems are very involved, but there are very interesting ways you can use them. So what I'll do is the following. Yeah. Okay, so what is it I'm after? Sub-exponential. By sub-exponential, we mean that 2 to the little o of k. Okay, step 1. Use theorem 2. Or maybe, no, I'll write a better theorem and then we will. Yeah, so here is a better. So in general graphs, we saw that if the vertex cover is at most k, tree width is at most k, right? Similarly, if a feedback vertex set size is at most k, tree width is k plus 1 at most. Now I want to refine it on planar graphs and say something stronger. G is planar and has vertex cover or feedback vertex set of size most k. G has tree width at most order square root of k. Okay, let's prove this. But if I prove this, do you see a sub-exponential FPT algorithm now for feedback vertex set using theorem 2 and the dynamic programming we have seen? So what do? K to the square root k, right? I run theorem 2 and check whatever this big O is. Let's say some c that comes out. Okay, we'll do our calculations. It'll turn out to be some c times root k. So I'll run my theorem 2 and ask, tell me whether the tree width of this given graph is strictly more than c root k. If it says yes, then I am done. Because of this theorem, I can say it's a no instance. Otherwise, in whatever 8 power square root of c square root of k time, it will give me a tree decomposition of width some order root k. I apply my dynamic programming algorithm root k power root k, which is like a 2 power root k log k, and get a sub-exponential, right? So let me write that down, and then we'll come back and prove this. maybe if anybody is actually can see the algorithm. Now think of the proof of this using that theorem. So algorithm using theorem 2, check whether G has tree widths greater than C root k. If so, return no. Else, use DP algorithm to find the minimum solution, right? And how much time? This gives me, it's like 8 power order root k, and this is like a root k power order root k. So overall, it's like a 2 to the power order root k log k, right? Little of k with polynomial factors I'm ignoring. If so, return no. And why is this correct? Because of that theorem. Okay, so what is the proof of the theorem? Right? If G has tree width greater than C root k from that excluded theorem on planar graphs, G has some, I'm going to write this as some d root k by, because there is a linear dependence between the tree width and the grid size. So, if it is C root k, I'm going to write some d root k by d root k grid as a minor. What do I have to show? Upper bound or lower bound? Lower bound. I want to show that if G has large tree width, the vertex cover or FES must be large. It must be because this grid is sitting there. How many, what is the vertex cover size of the grid? Or what is the FES size of the grid? Right? Size of minimum vertex cover on a T by T grid, or so vertex cover. Well, we just find a large matching. So it's omega t square. That's all I care about. Right? If you have a T by T, I mean, there are many ways to talk about it. One vertex can cover at most 4 edges. Right? The graph has, it's a T by T grid, so there are T square vertices and about order T square edges, because the average degree is like 4, except for the boundary vertices. So order T square vertices and T square edges are there. But if you pick any vertex, it can cover at most 4 edges. So you need omega T square vertices to cover all edges. Same with the feedback vertex set, because there are lots of disjoint cycles. Right? We have a T by T grid, it will have something like a T by 4 disjoint cycles. You pick some 4 edges, another 4 edges, and so on, and you can have omega t square different disjoint cycles. So it's omega t square. So to cover this grid, you need omega t square, which is like omega some d times k. So if you choose your d large enough, then you need at least k vertices to cover the grid. But there is one little piece we need to complete. This is not a subgraph, but a minor. Okay, if it is sitting as a subgraph, then it's easy, right? Yeah, this subgraph requires a lot of vertices and edges, so the whole graph requires it. But it's true for minor as well. So what is it we need to show? So we need this little lemma. If H is a minor of G, let's use the symbol for minor, then size of the minimum feedback vertex set is less than k. And similarly, if you replace this by vertex cover, that's clear, right? Because so how do you obtain a minor? You delete some vertices, delete some edges, or contract some edges. Clearly, when you delete vertices, the vertex cover size is going to go down. When you delete edges, sure, because you have fewer things to cover. But when you contract edges, you can still argue that that edge is gone, but you maintain everything else. But at least you've lost one edge, and this vertex can cover whatever those two vertices were covering. So this is an easy exercise to show that if you have a big graph whose feedback vertex set size or vertex cover size is at most k, then if you have a minor, that also requires at most k. So now we are using a contrapositive is that I have a minor which requires lots of vertices to cover. So the original graph requires lots of vertices to cover. And what is this lots? T for us is some d times root k. So omega t square is like some d square times k. If d is chosen large enough, then d comes out of this grid minor theorem. So you choose your c large enough so that t becomes large enough, then the whole graph has whatever this size greater than. Okay. So this is impressive that for a number of these parameterized problems or even the minimization problems and planar graphs, we can solve it in sub exponential time, and all we needed was this big black boxes, the grid theorem, dynamic programming on bounded tree width graphs, and this that if you don't have large, if the tree width is large, the answer is no. And the large here for general graphs it was some ck, here it is c root. Now, so now you can see that this is actually a general machinery, right? What did we need? We need the fact that whatever the parameter you are thinking of, if it is large on a grid and you have a dynamic programming on bounded tree width, you can put them together and get some sort of a sub exponential time FPT outcome. If it is large on a grid, then if the tree width is large, it has a large grid minor. Oh, you also need a lemma like this. It's large on a grid. So what are the things we need? Large on grid, dp on bounded tree width, and minor has large solution implies G as large solution. If you have all these three, then for such parameter, any parameter for which this is true, then you have a sub-exponential FPT algorithm on planar graphs. Because large on grid tells you has that the tree width has a square root dependency basically. Okay. Now, one example where this lemma fails is, for example, for dominating set. You can't say that my graph has a small dominating set, but I zoom in on a minor, it should have a small dominating set. It may not be, because even for subgraph this is not true. Even for subgraph this is not true, because somebody outside may dominate this whole thing. Okay, but for to handle that kind of thing, there is another excluded grid theorem, which has a slightly larger dependence on T, H contraction. So, planar G is planar, connected, and has tree with at least this. Then G has a T by T, not a minor, as a contraction. Actually, it fails only for subgraph. It's okay for contraction. Okay, so if you contract edges, the dominating set size actually becomes smaller. But if you delete edges, then it doesn't work, right? So this is a stronger theorem. Well, the bounds are slightly weaker, but it says that if it is planar and connected and it has tree with large, then it has a large grid as which you can obtain by doing only contractions. So you can't delete vertices, you can't delete edges, but if you are allowed, so you can obtain it by contracting edges. Now this theorem is useful to show that in planar graphs, even dominating set has a sub-exponential FPT algorithm, because you have this kind of a contracting thing, which if tree width is large, you will have this kind of a contracted grid, which requires a large dominating set inside, and so the original graph requires a large dominating set. Okay, so I'll just put in this buzzword. It's called bidimensionality. It has to do with this grid somehow. So using this notion of bidimensionality, which basically says that if you have a parameter which is large on a grid, it has a bounded tree width graphs as a dynamic programming, and if minor or a contraction has large solution, then G has a large solution. Then using this, there is a whole lot of problems: vertex cover, independent set, dominating set. Scattered set, induced matching, or center, feedback vertex set, longest path, longest cycle, connected vertex cover. A whole lot of problems have a sub-exponential. So vertex cover, independent set. On planar graphs, maybe there is some log K FPT. Okay, I mean, you've seen the big templates, except for this specific dynamic programming algorithm we have not seen, and the proof of these theorems, but you can just use this as a nice template to do design lots of exponential FP theorems. And it turns out it's not just planar graphs. This grid theorem is extended for even some larger class of graphs, and so many of these results go through for such larger classes of graphs. So these proofs are of these little theorems are quite involved. Okay, I think that's sort of a one round of tree width and how we can use tree width. So now let me give you a different view of tree width, which is not which is sort of easy to remember. And I mean, tree width as such, you have a graph and somehow magically you are going to get this tree decomposition. How do you get this tree decomposition is a magic unless you get into the proofs of this theorem and figure them out. But here is a hopefully a non-magic way of defining tree width. So I will I'll give you the big picture and then we'll get into the proofs next time. So let's talk about, so what is a K tree? So here's a notion of a K tree. So start with, so let me just do a 3 tree. So start with a click on 3 vertices. Then I'm going to pick a vertex and choose some 3 vertices which are already existing and add edges to it. In this case, I had no choice. And I pick a vertex and decide to add it to these 3 vertices. Pick a vertex, I add it to maybe these 3 vertices. New vertex, I add it to these. Keep doing this, and what I get is what is called a 3 tree. Okay, so what is a K tree? Start with the K click. Start with the K click and let's say V1, V2 to Vk. Vn, so K click on n, K tree on n vertices. Attach Bi or join Bi to some K vertices of V1, V2, Vi. And what you get is a K click, a K tree, sorry. So what is a one tree? Can you get every tree like that? Okay, so you can prove by induction. Yeah, so one tree is a tree, standard tree, because you just start with one node and then attach one node to it, and then basically I'm adding leaves to, I choose some vertex to which I will attach it. I don't necessarily get only paths, right? Yeah, every tree can be obtained like this. So one tree is a tree. So prove this, right? What do you mean by this? That of course what you get is a tree in this process, but what I am saying is actually exactly the class of trees. Every tree can be obtained like this. Okay, so you can easily prove by induction because every tree has a leaf, remove it, the remaining is a tree, use induction hypothesis you obtain by this process and take that vertex and attach to somewhere. Let us define a partial K tree. It's basically a subgraph. Just delete some edges out of your K tree and what you get is a partial tree. Subgraph. So here's a nice characterization. Graphs with tree with at most k are exactly partial K trees. So we'll show this next time. It's doable. It's not hard. It's nice. So yeah, before that, let's yeah. So we'll get to that next time. So let me just change track and talk about the following: simplicial ordering of the vertices of a graph. Or okay, it's called a perfect elimination order. Okay, so I'll write this. Whatever I'm going to do, will slowly build towards it. Perfect elimination so it's an ordering of the vertices such that neighbors of Vi intersection the induced subgraph on that is a clique. So what am I saying? So it's an ordering of the vertex set of the graph. It may or may not exist. So if you look at any I and look at all edges to which it's adjacent before, these neighbors form a clique. The neighbors of Vi intersection V1 to Vi minus 1. I don't care about its neighbors the other side. Its neighbors this side. You take those vertices and look at the induced subgraph, they form a clique. Okay. Now, it may or may not exist for a graph. So let's look at an example. So let's see if I can I order vertices okay, let's add this edge. A, B, D, C, is it? Okay. So, if I order them as A, B, D, C, then B is adjacent to A, fine. D is adjacent to A and B, but A, B forms a clique, and C is adjacent to A, B. C is adjacent only to B and D, and B, D forms a clique. Good. So, here is the graph where I can order it this way. But suppose I did not have this edge. Can I now order this in a way that one vertex should come last, okay, and right, the last vertex, the neighbor should be before it, and they have to be adjacent. Here, no neighbors are adjacent, so it cannot. So, this does not have, so it's called PEO. Whereas, when I added that edge, it had perfect elimination ordering. Now, there are a lot of questions. Which graphs have perfect elimination ordering? Why do I care about this perfect elimination ordering? It turns out perfect elimination ordering is useful to solve a number of hard problems, clique, independent set, vertex cover. You can, if you have a perfect elimination ordering, you can actually solve these problems very efficiently. And you can actually build a tree decomposition if you have a perfect elimination ordering by looking at these neighborhoods gradually, and I will get to K trees and getting to this. Okay, but here is a, I mean, from this observation, so let's define a class of graphs, a very important class of graphs called chordal graphs. If every cycle C of G of length greater than 4 has what is called a chord. Okay. So, chord means edge joining non-adjacent vertices of the cycle. So, basically you do not have a large induced cycle. Okay. If you have any large cycle, there must be some edge between two non-adjacent vertices. This example actually shows that if you have a perfect elimination ordering, it must be chordal. So basically, right. So, is the definition clear, right? So, I cannot have such a cycle in the graph unless I have an edge like this. Now, I can't even have this cycle, so I should have an edge like this. Okay, I cannot have a cycle without chords. Now, here let me just end with this following little theorem, because we have already sort of seen the proof. G has a perfect elimination ordering implies G is chordal. What is that? You actually had the proof when we were talking about that. Okay, so
if you look at any cycle,
okay,
look at the vertex that appears last in the perfect elimination, its neighbors must be. Okay.
yeah. So assume not. Suppose you have a chordless cycle, right? And somebody has given you a perfect elimination ordering of the entire set of vertices. So pick the last vertex of this cycle in that ordering. Because it's a perfect elimination ordering, its neighbors before form a clique, which means the neighbors of that vertex in that cycle must have a chord. So your assumption that it's a chordless cycle is wrong. Okay. So, it is a simple proof. Now, it turns out this is also true. That if it is caudal, it has a perfect elimination ordering. The proof is a little more involved, but so having graphs having perfect elimination ordering are exactly caudal graphs. So, what we will show next time, we will show the converse. We will see the use of perfect elimination ordering. If you have perfect elimination ordering, you can solve some hard problems in NP hard problems in general graphs easily. And then we will show that if you have this here, if you have a partial K tree, then it is actually a subgraph of a caudal graph. Then we will use the perfect elimination ordering and then design a tree decomposition. That is one direction. The other direction is not very hard. So, we will get to all of this and important use of perfect elimination ordering next time.